Good afternoon, everyone. You are in for a treat. We have a special guest presentation today by Professor David Kaiser from MIT. He is an award-winning educator and author, and also a professor of both physics and the history of science. He has written a number of books and articles, including How the Hippies Saved Physics, Science, Counterculture, and the Quantum Revival. So please put your hands together and welcome Professor David Kaiser.
Thank you so much. I'm really just delighted to be here today. I want to tell you about a quantum adventure, an adventure I was very lucky to get to participate in just a year ago. A year ago, I found myself on the top of a mountain in the Canary Islands, just off the coast of Morocco, off the coast of Africa. I was working with some terrific, very inspiring colleagues from many different countries. We were using some of the largest telescopes in the world. We got to use those beautiful telescopes to gather light from distant galaxies called quasars. The light from some of those quasars had been traveling toward the Earth for most of the history of the universe, almost since the time of the Big Bang itself. And we used all those tools to try to test one of the most strange, really most curious features of quantum theory, this notion called quantum entanglement. And I want to tell you about the test that we conducted. But first, let me back up. What is quantum theory? Quantum theory is wonderful. That's the first take-home message for today. It's a scientific theory about how matter behaves at the smallest scales. When we zoom down to look at the size of atoms or parts of atoms. Using quantum theory, we can describe the structure of an atom, how the parts are arranged in space, how they might change over time. Quantum theory is also the single most precise scientific theory in history. It's remarkable. There are certain properties we can calculate with the equations of quantum theory. We can compare those answers with tests that are done in real experimental laboratories, tests on real materials like atoms and parts of atoms. And for some of those quantities, the theoretical predictions and the experimental measurements agree to 12 decimal places, to 1 part in a trillion. That's pretty astonishing. That's like being able to predict in advance the exact distance between the Museum of Science, in fact, from that bench right here within the Museum of Science, the distance between that and a particular crater on the moon, and to get the answer right to within the width of a single human hair. That's what it's like to have trillionth accuracy. It's a marvelous, incredible achievement. It's also pretty strange. It has a series of strange features that physicists have wondered about, argued about, scratched our heads over for about a century. But probably the strangest of all of these is a notion called quantum entanglement. Entanglement suggests, at least in terms of quantum theory, it's a prediction of the theory, that in certain situations, pairs of particles can become so strongly interconnected, so connected to each other, that something that might happen to particle A over here could instantaneously have an impact on the behavior of particle B, no matter how far apart particles A and B had become. Now that's pretty strange. Ordinarily, we imagine if we have 2 particles A and B and they've separated apart from each other, if something happens to particle A, we would expect it to take some time for information, some influence, to travel across space from where A was to finally affect particle B. That's how things ordinarily work when we think about throwing a baseball or any kind of ordinary physics that we're used to. Quantum entanglement suggests instead that there could be an instant connection, no time taken at all for that influence or information to travel across space. That is so strange that Albert Einstein himself rejected this notion. In fact, he helped identify this as a theoretical prediction, and he said in the end, if that's what the theory predicts, the theory must be wrong. Things can't really work that way in the real world, concluded Einstein. He wrote a very famous, very careful analysis with 2 younger colleagues. They went through the arguments very, very carefully, and they published their conclusions saying, if quantum theory predicts entanglement, quantum theory must be wrong. That simply is too strange to be true. He had a series of very intense debates with close friends and colleagues like Niels Bohr. They debated this for decades, literally for decades, and neither side could convince the other. In the end, late in life, Einstein said, "This stuff is spooky action at a distance. It's just too strange to be true." Well, soon after that, a younger physicist came along named John Bell. And Bell revisited these debates. He went over all the calculations that Einstein and his colleagues had done, and he realized that Einstein had made a series of assumptions. That when Einstein rejected quantum theory because of things like quantum entanglement, he'd had very particular ideas in mind. One idea, as Bell clarified, was that Einstein assumed that each particle has a definite set of properties on its own, even before it might be measured. You can think of that as like saying each particle, particle A and particle B, carries with it a little instruction manual. It has a manual, a logbook with it, wherever it zigs and zags through space. And in that instruction manual would be the answers to any question that might be asked of that particle. So if we wanted to say, measure, what's the value of your spin, it would look in its instruction manual and say, oh, spin up. Or any question we might ask. And that's like assuming the particle had a definite value for all these properties, even before we might choose to measure them. Separately, a second assumption that Einstein had made was that nothing, no influence, no force, no bit of matter, could travel across space infinitely quickly. And that's like the intuition we described before. If something happens to particle A, it must take some time to move to particle B. That was Einstein's second major assumption here. It was on the basis of those assumptions about how matter behaves, about how forces must travel. On those assumptions, Einstein said quantum entanglement can't possibly be real. Well, John Bell came to a different conclusion. He said these are actually assumptions. They might be true in the world, they might not be true in the world. What if we try to test and find out? So Bell invented a way to try to test whether entanglement is a real feature of the world, as predicted by quantum theory, or whether Albert Einstein was right after all, and this prediction is off base. So we call these now, in Bell's honor, we call these Bell tests. So John Bell realized we could pose a series of questions to these particles, to particle A and particle B. The questions could be of many kinds as long as they had the following form, that for each question we asked, there's only two possible answers. Heads or tails, up or down, yes or no. Whatever question it is, as long as we can put it in the form where there's only two possible outcomes for that question. And so in our log books, we could code those as an answer of +1 or -1. If it's a question of that form, John Bell said, we could really test how the world works. He said, let's come up not just with one question of that form, but two questions, each of which have only two possible answers, +1 or -1. Bell then said, what if we choose randomly, by some random process, which question gets asked of each particle? If we can do all that, isolate two questions, each of which has only two possible answers, and decide randomly, like by flipping a coin, which question gets asked, then we can compare how often the answers to these questions agree between particle A and particle B. Remember, what we're writing down are just a series of +1s and -1s. Their answers have only two possible outcomes for each question. How often do the answers agree, even when we choose which question to ask at random? And Bell showed in a beautiful, very elegant analysis that if Albert Einstein were right, if those two assumptions really are true of our world, then this comparison can only show the answers agreeing so often. Sometimes they'll agree, maybe by chance. Sometimes they won't agree, but there should be an upper limit to how often these answers will agree when we do the comparison. Bell went on to show that unavoidably quantum theory predicts something else. That quantum theory says these particles should have a stronger connection. Their answers should agree even more often if quantum theory describes the world rather than Einstein's assumptions. So that sounds pretty abstract. I like to think about entanglement in terms of the following story. I imagine a pair of twins, a boy and a girl. Alice comes to Cambridge, Massachusetts. She comes to study at MIT, I like to think, while her brother goes in the other direction and goes to study in Cambridge, England. Soon after Alice arrives in town, she goes to a neighborhood restaurant. The waiter says, "What would you like for dessert?" That's pretty good. That's already physics is getting better, right? You can have a series of desserts. That night, he says, you have a question to answer. What type of baked good would you like for dessert, a brownie or a cookie? And now to put it in the form of this test that John Bell devised, we can say that he'll write down in his ledger, in his logbook, a +1 if she answered that particular question with a brownie, and he'll write down a -1 if she chose a cookie. Now, little does she know, across the ocean, her brother Bob is encountering a different waiter in a different restaurant thousands of miles away, and he happens to ask Bob the same question. What type of baked good would you like for dessert? +1 for brownie, -1 for cookie. They come home for Thanksgiving to compare their answers. Turns out the first night they were there, they both happened to order a brownie. Well, that could happen. It's a random process. They both felt like a brownie that night. Maybe that's not so surprising. But they go on. The second time they both went to the restaurant, they both ordered cookies. And then both cookies and both brownies, both cookies, both brownies. This is now starting to look pretty spooky, right? They're thousands of miles away, being asked this question. They're answering with what looks like random at each side, and yet their answers are lining up. Alice and Bob each chose the +1 answer and the -1 answer equally often. In fact, it looks like in a random order. Sometimes Alice got a brownie, sometimes she ordered a cookie, but even though what looked like randomness at each side, if you just looked in Cambridge, Massachusetts, or just looked at Cambridge, England, you wouldn't notice much of a pattern until you compare them. And you see they were lining up perfectly every single time. Now, how could that happen? It's a fair question to ask, how could that happen? The most obvious thing would be to say maybe they're communicating. I mean, if we're ordering desserts, everyone knows you whip out your phone, you take a photograph, you post it, you tweet, #quantum_desserts, right? Maybe they're communicating, and maybe it's not so strange at all that Alice and Bob are ordering in the same thing because maybe they have a way to coordinate their answers. So my colleagues and I wanted to test whether that's what's happening in entanglement, and here's a photograph of her actual setup on the mountaintop on the island of La Palma in the Canary Islands. I want to draw your attention to 3 parts, 3 stations that were really central to our experiment. I'm going to talk first about this middle one, the transmitter station. We weren't using actual human twins who ordered desserts. We're using specially prepared particles, little particles of light called photons. We made twins, we made entangled photons in the following process. Inside that little experimental station, we had a high-powered laser, which is pretty cool. It shoots out light of a particular shade of purple. We shine that into a special kind of crystal, very clear. It looks like a clear piece of plastic. This has this special property that when light of just the right shade, just the right color shines into that crystal, the crystal will absorb that incoming particle of light, it'll eat that one up, and it will shoot out a pair of particles that have half the energy of the incoming particle. So you shine purple light in, and out come pairs of particles of a different color, and those will play the role of our twins. These are entangled particles, Alice and Bob. They're born together like human twins would be. We then transmit those across the island, almost half a mile in each direction, in opposite directions. When the particles get to their destinations, that's where we have our detectors. That's like the waiters at the restaurant who want to record their orders. So they've traveled across a good chunk of the island. We're about to ask questions of them with our instruments. That's like the waiters taking dessert orders. What's important to note is that light travels really, really, really quickly. These are particles of light. So the entire process of creating the particles in that middle transmitter station, having them fly through the air at the speed of light, actually complete a measurement of them, receive them, measure their property, that whole process takes just about 2 millionths of a second, 2 microseconds, just about, in each direction. Why is that important? It turns out because these stations are so far apart from each other, it would take almost 3.5 millionths of a second for even a single light beam, a single tweet or Facebook status update or any kind of message we can imagine. It would take almost 3.5 millionths of a second to travel from where Alice is being measured to where the Bob particle is being measured. There's no time in this experiment to have sent an update to say, I just ordered the brownie, you should order one too. Right? We've asked the questions so far apart from each other, there's no time for a single signal to have helped them coordinate their answers. That was pretty cool. So how could they keep giving the same answer in our story with the brownies and the cookies? It can't be that they're communicating. We've ruled that out by the design of our experiment. But Einstein, if Einstein were alive, he would say, oh, but there's another way we can explain that. Maybe the 2 particles, our twins, Alice and Bob, had actually worked out a plan ahead of time when they were still in the station, before they left their house, let's say. Maybe they said, well, on Tuesdays, Thursdays, and Saturdays, just make sure you order a brownie. Our answers will line up. If they could have coordinated when they were still together, then it might not be so mysterious why their answers line up. They could have coordinated, in other words, their instruction manuals. They're going to write their manuals together, they're going to leave, but carry their manual with them, and of course their answers will continue to line up. So how could we rule out that kind of possibility? How could we see if Einstein's right or if quantum theory really describes the world? This is really the genius of where John Bell's tests come in. We add that second question, right? Remember, Bell tests involve two different questions that we could ask of these particles. So in our story, instead of asking only about baked goods for dessert, sometimes the waiters ask about frozen goods. First of all, again, great story, right? All you get is great, delicious desserts. Sometimes the question is, would you like an ice cream sundae or a frozen yogurt? Other times they say, would you like a brownie or a cookie? Again, we can code those with our +1 and -1, only two possible answers to that question. If Alice orders the ice cream sundae, her waiter writes down a +1, okay? The waiters on each side are trying to determine which question to ask by some random process, sort of like flipping a coin before they come out and present the question to their particle. And now we look at the kinds of answers when we have two questions in the mix. Sometimes, by this random process, both waiters will pose the same question to each particle. They'll both be asked question 1 about baked goods. What happens in that case? Well, it's like what we already saw. Both Alice and Bob will wind up each ordering the same thing, both brownies or both cookies. When they're asked the same question, question 1, they give the same answers, just as we saw the first round. Sometimes, by chance, Alice will be asked question 1, but Bob will have been asked question 2. And again, we find a very curious pattern. It's not entirely random how the results shake out. When there's Alice asked question 1, Bob is asked question 2, Alice orders the brownie at the same time that Bob orders the sundae, but not the frozen yogurt, right? Or she orders the cookie while he orders the froyo. They're lining up, they're correlating when they're asked different questions. And sometimes they're both asked question 2. Sometimes the waiters have done some random process and both sides happen to ask at the same time that second question about the frozen desserts. Now, Alice and Bob give opposite answers. If they're both asked question 2, Alice takes the ice cream, Bob takes the froyo, or vice versa. So now this is starting to be pretty strange, right? How could their answers coordinate this with this kind of pattern? What's happening is the way that Bob answers the same question about frozen dessert seems to depend on what just happened an ocean apart with Alice. If Bob had an instruction book saying if you're asked question 2, order the frozen yogurt, that won't work anymore, right? Any single instruction manual that Bob could have carried with him doesn't seem like it could address each of these possible combinations. He would need to have more information on his side to determine how to answer the same question, that question 2. That's the genius, I think, of these Bell tests. Now, how could that happen? Right? How could we account for this kind of behavior when we're testing real particles and not just imagining people ordering desserts? Let's go back to the setup of our experiment. We have that source of entangled particles, the laser and the crystal, and they shoot out. We have detection stations, instrumentation to ask questions and record the answers, like our waiters. We assume that there's some random process for the waiters to determine what question to ask, what measurement to perform. So what if we actually hadn't realized it, but some third party had tampered with that seemingly random process? Maybe they'd substituted ordinary coins with sort of special coins that come up with a special pattern, trick coins. What if they tampered with that random process and then tipped off Alice and Bob before they even left their home, right? So maybe there's some other process that meant it wasn't actually random after all, about which questions get asked in which order. If Alice and Bob could have gotten a preview of the question list, like a student getting a copy of a pop quiz the night before, right, then they'd know the questions that we asked in which order. Maybe Alice and Bob coordinated their answers with that extra kind of preview. Maybe they were tipped off. That would be at least a way that an Einstein-like world could account for this kind of pattern. So how do we test for that? Here's where finally the quasars come in. Quasars are beautiful, enormous, bright galaxies, very far apart from our own galaxy, the Milky Way. They're very far across space. In fact, some of them are so far away that the light that we receive on Earth has been traveling for most of the history of the universe, almost since the time of the Big Bang itself. For 10 billion years, for 12 billion years, they are very, very far away. So what we wanted to do, we go back to our experiment here, we were using these enormous, amazing telescopes on each side where the waiters would have been stationed to make these measurements. We had two of the largest telescopes in the world that we were very lucky to be able to use, the Galileo National Telescope on one side of the island and the William Herschel Telescope on the other. Each of these inside has a 13-foot mirror, 13 feet across, polished nearly to perfection. They're enormous, enormous. So they can gather light from so far away, from such dim spots on the sky, that they can measure light from things like very distant quasars, very distant galaxies. So we call this a cosmic bell test. We're going to ask questions of our particles on Earth, but we're going to take inputs from the sky, from very far away in the cosmos. So it turns out when we measure the light from these quasars in very short fractions of a second, very quick measurements of that distant light, sometimes it'll look a little more blue than average, and sometimes that light will look a little more red than average. And it'll oscillate, it'll switch back and forth in basically a random pattern. Sometimes blue, blue, red, blue, blue, red, red, red. It's very, very random, and yet it switches on a very short time scale, fractions of a second between looking more blue or more red. So we opened up these gorgeous telescopes, looked at a particular quasar in the sky in this direction, a different quasar in that direction. If the light that we measured in that split second were more blue, then that would instruct the machinery at that site, our detectors, to ask question 1 when the entangled particle arrived. That would be like telling the waiter what question to ask. Instead of having him flip a coin in the kitchen, he would measure light from a distant, distant galaxy in that fraction of a second. That would all be happening while the entangled particle was traveling across the island. So we emit the particles, we then wait, they've left their home, they've left that transmitter station. We take an immediately quick snapshot of that quasar. Was the light blue? Okay, ask question 1 when that particle arrives. If the light happens to be red, ask question 2. So now there's no way to have tampered with or even predicted in advance the pattern of questions to be asked. No one could have gotten hold of those distant galaxies because the light that we're measuring was emitted before there was a planet Earth, and in fact, even in some cases, before there was a Milky Way galaxy. That light has been traveling for most of cosmic history, and we just receive it that split second. We did this with 20,000 pairs of particles, 20,000 pairs of twins, Alice and Bob, on the mountaintop. We looked carefully at how their answers were arranged when we compared their answers, even when we had asked different questions. We found exactly the correlations, the lining up as predicted by quantum theory. We found evidence of quantum entanglement and not the sort of lower level of correlation that would have held in Einstein's world. We found the predictions of quantum theory remarkably clearly on display. So what? So what? Remember, I told you Bell had clarified Einstein's assumptions that had led to Einstein assuming entanglement couldn't be real. Einstein had assumed that these particles have definite properties, like their kind of personal instruction manuals they carry with them. And he'd also assumed that nothing can travel faster than light. Those both seem like very reasonable, very straightforward things to assume about our world. And they can't both be true. Experiments like ours and others from other groups around the world, they lead us to this very troubling and very surprising conclusion. These two very straightforward sounding assumptions, those don't operate in our world. Either one is wrong, or the second is wrong, or both are wrong. What we know is they're both not correct. So we've learned something deep and really very fundamental about nature by asking this funny series of questions of two entangled particles. There are other reasons to keep asking this question. One is a brand new technology called quantum computers. These quantum computers use entangled particles, little miniature Alices and Bobs, to do computation, and by doing that, they can be exponentially more powerful, exponentially quicker than even the fanciest supercomputer today, and we'll actually have this very quantum computer here in the Museum of Science later this spring. Come back and see the quantum computer in April. There's another application that colleagues of mine are already pursuing, and that's to produce a secure communication channel, again, using these entangled particles. It's called quantum encryption. Right now, over our heads, there's a satellite orbiting the Earth. It's already happening now. The satellite is beaming down pairs of entangled particles, much like the ones that we used in our experiment. But now they can be measured not a mile apart, but thousands of miles apart. In fact, there's receiving stations in Europe and in China, and soon there might be many, many more. Because of the special connectedness of those particles, people can set up a secret code because no one else knows how their other particles would have answered this series of questions. They can set up an encryption key, and now people can set up a secure means of communicating really across the entire world. That will only be secure if entanglement is real. We wanted to know for as sure as we could that this happens in the world and is not only a theoretical prediction. So I hope I've convinced you that cosmic bell tests help us learn about the most fundamental behavior of the world, the most basic laws of nature, and also they are a lot of fun. So if you want to learn more about this topic, I encourage you to search on YouTube. There's I think a very nice documentary that just came out called Einstein's Quantum Riddle, describes these things in a bit more detail, has footage of our actual experiment and other really exciting things going on. There's a series of books that colleagues of mine have written that are very fun, and I think they explain these things quite well, very kind of carefully and I think a very accessible way, almost no mathematics. And I also encourage you to come back to the museum in early April, where you can learn even more about quantum theory, quantum entanglement, nanotechnology, quantum computers, all these amazing things. So come back here in early April. Thanks so much.
Well, thank you so much, David. That was wonderful. Let's have another round of applause for Professor David Kaiser.